About exponential functions and then logarithms to follow on from that. But for today, exponential functions. To really get our heads around what an exponential function does, we first need to make sense of exponential growth and exponential decay. These are terms that sometimes get kind of thrown around, loosely, just to mean like something happens fast, right? Like, like a news article or whatever, like, oh, this, it grew exponentially. Like, they don't really mean that most of the time. What exponential growth or decay really means is types of change where we can think of things happening in terms of multiplication. And multiplication, of course, is really the same thing as division, right? So in terms of multiplication or division. So if multiplying, then growth. If dividing or multiplying by a fraction, then decay. And my go-to sort of pet example for this is the zombie apocalypse, of course. Somebody describe for us how the zombie apocalypse, works. Okay. Right, like we've seen zombie movies, right? Somebody gets bit, and then everyone, they try to hide it, and everyone's like, "Oh, you're looking a little gray there, Charlie," and then all of a sudden, Charlie's trying to eat your face, right? So the people are people, the zombies are zombies, but then the zombies bite the people, and the people turn into zombies, and so if we model this by thinking about, okay, you know what, we're going to put a little structure on this. Zombies, you all go out at 3 o'clock every afternoon and you bite somebody, right? Like that's what you get to do. So if we suppose that the number of zombies doubles each day, of course, as usual, like we're sort of oversimplifying some stuff. Not that we like really model zombie apocalypse, but it's not all that different than modeling like spread of a virus or something. There was a while there we're talking about the zombie apocalypse here was a little less fun, right? But like we've got some distance now, right? So if every zombie goes out and bites one other person, that one other person turns into a zombie, then and let's start, just to make some stuff work, let's start counting. Start with like day 0 is when we count. Excuse me. So there's one zombie, I don't know, something happened in the lab or, however these things start, right? Some kind of curse, whatever. There's one zombie. The next day, that zombie goes out and bites one additional person. So now there are 2. And so on and so forth. The next day, if there were 2, they each go out and bite one other person. Now there are 4, then 8, 16, 32. Because if what we're doing to get from one step to the next is doubling, sorry, I didn't really have a plan for where that sentence was going to go. I started it with an if, I don't have it then. What we're doing from one step to the next is doubling, right? And you can kind of see how then this grows really quickly. And so on, right? Okay, so exponentials work like this, where to get sort of one full step in time, right? Think of this as like your x value, right? What day is it? It's day 5. Okay, how many zombies are there? There's 32 because I doubled 5 times, and that's where it puts me, right? So each time I take a full step in the x value, what happens to the y value is I take the previous one and double it, right? Multiply it by 2. This is kind of like the way you do like slope for linear functions, right? For a linear function, say you've got, slope 3. Well, you go from one point and you count up 1, 2, 3, and go over 1 to get the next, right? And then you go up 1, 2, 3, and over 1 to get the next point, and then you get a nice straight line. What you're doing there is adding over and over again the same value, right? And that's why you count up 3 and over 1, because you're just taking a full step, right? Here, what we're doing is related but not the same, because instead of adding, we're multiplying, right? But the idea that, for a linear function, you have a constant growth rate where the way I think of the growth is additively, right, by counting up. Here we have a fixed growth rate, but I think of the growth rate multiplicatively by multiplying, right? That's what an exponential function is. What would be a shorter way to like represent what's going on here rather than saying, hey, what's this step? It's 2 times 2 times 2 times 2 times 2. What would be a shorter way I could write that? 2 to the 5th. And then you see why they're called exponential functions, because you can write them as an exponent, right? An exponent in the like normal, whole number power sense is just shorthand for that many copies of whatever the base is, right? 2 times 2 times 2 times 2 times 2, 5 copies of 2 multiplied together. Well, that's a lot to write down, so instead we write 2 to the 5th. So the way we could represent a thing like this then, if I think of these as being, sorry, it's the same color. If I think of these as being x values and these as being y values, I could write that y, the number of zombies, equals 2 raised to the x. And now if you want to know what 2 to the 7th is, or sorry, if you want to know what happens on day 7, I can find 2 to the 7th, and 2 to the 7th is 128. So instead of needing to like build it from scratch, right? Because what I'm doing here, just sort of listing them in a table, if I want to know what day 10 looks like, I need to take what I already have and go, okay, times 2, 8, times 2, 9, times 2, 10, right? Like I have to build the stuff in between. A function that represents that means I can go directly to, hey, what's 2 to the 10th? That's what things look like on day 10, right? This is an example of an exponential function. The thing that makes an exponential function is that you have a constant base and a variable exponent. So that's how these are different than all the stuff we've looked at before. We've done tons of stuff with powers and exponents on it, right? But it's always been variable raised to a power, right? Like think about the test yesterday, right? One of the questions had you rewrite something like x to the 2/3. It's a variable raised to a constant fixed power. Now we're switching that. We're saying, okay, well, what if the base was the thing that was fixed and the power was the thing that was changing? Okay, does that make sense? Okay. The growth rate here is doubling, right? That means the base is 2. The way that changes, if say instead of the number of zombies doubling each day, if it tripled, right? So each one goes out and bites 2 and infects 2 people. So you go from 1 to 3, and then from 3 to 9, and so on. That would change what you multiply here, how you get from one point to the next. That would also affect the base then, right? So the base tells us about the growth rate, right? This is doubling, so the base is 2. Okay, that's exponential growth. If we have something that is instead decaying over time, then it's exponential decay. Decay would look like, you start with some number of things, and as you go along, it decreases. So a good example is something like a single elimination tournament. in the spring, this always lands like right around March Madness time, right? Like, so if you're into sports at all, picture like a tournament bracket, right? You start with, 8 or 16 or however many people or teams or whatever, and they play head to head, and the winner advances and the loser goes home, right? So if you start with, I don't know why I don't do it here. Let's say we start with 8, teams or players or whatever, right? So these are all the people competing in this tournament. The winner advances and the loser goes home, right? And then the next set of people meet. The winner advances and the loser goes home. Until finally you're down to 1, right? So if you look at tournament brackets like that, if it's single elimination, that's why, like the NCAA tournament, you have 64 teams. 64 is a power of 2, because then you can, reduce down to 1 without having to get into weird stuff. And if you look at brackets for things like college football playoff now is a good example. There are 12 teams this year, right? Well, 12 is not a power of 2, so things get a little squirrely, right? Some teams get a bye and some don't, and you have to change the rules a little bit to sort of accommodate the number of teams that are there. That's an example of an exponential decay. In this case, there are half as many teams as at the previous round. So the way I drew this, you start with 8, and then you go to 4, and then 2, and then 1. So the progression goes from 8 to 4, that's divided by 2, or times a half. From 4 to 2, that's again times a half. From 2 to 1, that's times a half. You would model something like this with a base of 1/2 then, right? Because that's how you get from one round to the next. That's how you progress. There's some other examples that we'll look at. Radioactive decay is a place where this comes up as well. So we'll do some other examples with where we see these things happen. But a lot of stuff, especially in the natural sciences, but also in like finance, like the way compound interest works, which is the thing that you very much want to know about for like your own life. Those are all modeled by exponentials. So we'll spend some time on those later on once we've got kind of some of the basic stuff out of the way. Okay, everybody good so far? Okay, right on. So what we need to look at today then, what we're going to concentrate on, and really this week, is modeling these things as functions. So what I want you to do is graph the function y equals 2 to the x. So we've already, plotted some points, right, in this this table that we made here. So you can plot those, graph it on the calculator, Desmos, see what it looks like, and find all the usual stuff, domain and range and intercepts and all that kind of stuff. Yeah, sorry. So you should be able to type in something like 2 and then find the like caret button for an exponent and then 2 to the x.
Yeah, but just, oh, okay.
Should do it. Here, I'll come take a look.
I know it's going like this, but like whenever I do, because I'm like going to
Oh, so just enter it in. So what you're telling it there is to grab like y equals whatever 2 to the 0 is. So you're doing a variable. So the graph's a function.
Oh,
Okay. And then if you want the single values, go to the table, and you can see, like a list of values. Okay.
Change the values from here and stuff. Like if I wanted this to be.
I don't think you. Yeah. There's a setting somewhere that you can change it so you can type something in. Never touch that.
Do you know how to do that on your define like values?
Yeah. So if you go second, then hit table.
Oh, wow.
Yeah.
Okay, there's
Yeah.
Okay, so there is the graph of this thing, right? Again, I threw a table on here so we can see some points as well. When we did the zombie thing a second ago, I started with 0 and 1, right? And then kind of built it from there. And again, you see like powers of 2 here, right? So 1, 2, 4, 8, so on. Notice if you go the other way though, like if you take a negative x value, 2 to the negative 2, for example, what does a negative exponent do? Reciprocal. So this would be 1 over 2 squared, or 1/4. So if you look at this point, and of course calculator gives it to you as like a decimal rather than a fraction, but if you look at this and this, there's a symmetry there, right? 2, 4, well 2 squared is 4. 2 to the minus 2 is 1/4, or 0.25. There's a symmetry in, it's the reciprocal, right? It's not the same value, but going to the left, the points that are going to show up if you plug in like integer values for x are going to be the reciprocals of the things moving out this way, right? So like -5, this would be 1 over 2 to the 5th, or 1 over 32, right? Okay, so the like nice points, right? The places where you plug in an integer value and evaluate the function are going to be powers of whatever the base is. But we know enough about exponents and powers. We've sort of expanded, right? In the last chapter, we talked about power functions more generally and how you deal with an exponent that's a half or 2/3 or whatever, right? It turns out you can take that even further and deal with things where the exponent's like really messy, where it's like an irrational number. But what happens is that we get this continuous function that includes not just those, right? Not just the nice points that are marked here, but also the stuff in between, right? As a smooth continuous curve that's all in one chunk. And first, we'll zoom it out a little bit. What's just your overall impression of this thing? Like, how would you describe what it does? Okay, yes. Rocket ship is a good description. Yeah, I think. I mean, this direction, if we're thinking in behavior, that direction is more or less flat, right? It gets very close very quickly to the x-axis because you're taking reciprocals of powers of 2, right? So they're always going to be positive, right? They're always going to be sitting just above because anything out this way looks like a reciprocal of the power of 2. So it's still going to be positive, but very small. The other direction, well, now you see why, we kind of take exponential growth as just a, catch-all term to mean things happen fast. Because these do grow very quickly, right? We're not even out that far, and like before we even get to 10, 2 to the 10th is 1,024. So these things grow very quickly, right? And now you see why zombies are a problem, right? Or more generally, viruses and things that spread quickly are problematic because, if they grow quickly, then you very quickly start to run out of people who aren't infected. That's bad. Okay, so initially slow, then very quick, right? Flat on one side, very much upward facing on the other. That's a good kind of general idea for exponentials, right? So exponentials basically look like this, right? I'm mirroring for you, so I guess it kind of looks like your right hand, but flat on one side and very quickly growing on the other. What's the domain of such a thing then? Mm-hmm. What about the range? 0 to infinity, because they only live in the upper half. Should 0 be included? No. Why not? We can't get there, right? Think about what that would mean. What power of 2 is exactly equal to 0? Well, powers of 2 are always going to be positive, right? So we can't actually reach 0. What does that mean about the x-intercepts? That there aren't any. Y-intercept? 0, 1. Because what's anything to the 0 power? 1. How's what work? Thanks to the 0 power being 1. One way to look at it would be this, right? To get 0, or well, here, let's think about it this way. If you take a like base and divide, what do you do with the exponents? Subtract, right? So that'd be 2 to the 0. But what's something divided by itself? 1. So that's why. It's a little bit by convention to sort of make all the other stuff work together, right? But anything to the 0 power is 1 because it has to be, because otherwise everything else falls apart. Yeah. That means then that this didn't have anything to do with the fact that the base was 2, right? The same thing would happen for other bases as well. So keep that in mind. Anything else that we think might be important here? I kind of alluded to it a second ago. What does this end do? It approaches, it flattens out, it's really close to the x-axis, but never quite gets there. What do we call it when something like that happens? An asymptote. There's a horizontal asymptote at y equals 0. Now, it works a little bit differently than the ones we saw for rational functions because it kind of only shows you what one end does, right? It only shows you the behavior on one side of the function, but it's still a horizontal asymptote. It still counts. It's kind of a half asymptote, which is both fun to say and kind of gives you an idea of what the thing does, right? So it's an asymptote that really only tells me about like one side of it, but it's still there. Okay. So that's about as good as we're going to get of a kind of general like model for what exponential graphs look like. Next thing is to see, how do these change? How do they vary? So these are all exponentials that have a different base, right? The base here was 2. Maybe I'll just write that in somewhere just for kind of emphasis. Base was 2. And we see, all this stuff happening. Now what I want us to do is look at changing the base and see how that affects things. So 3 to the x, 5 to the x, 1/3 to the x, 1/5 to the x. Graph those, one at a time, all together, whatever. But take a look at them, try to figure out, what's changing, what's different, right? What stays the same and what changes as we vary the base. We'll take 10 minutes or something for y'all to kind of work on that, and then we'll talk about it together. may already kind of be figuring this out, but you may want to start by looking at them kind of one at a time, and then maybe look at them together, so you can compare and see what's happening. Yeah, I mean, all this. Like, so what we're trying to figure out is, a way to reduce the amount of stuff that we're trying to remember, right? So we're trying to figure out, how are these things similar? How are they different? What does it depend on? Okay. All right, so that's 2 to the x. Let me copy of the domain and range stuff down just so we have to look at. Okay, so 2 to the x we figured out has domain, all real numbers, range just the upper half, not including 0. Y-intercept is 0, 1, and a horizontal asymptote y equals 0. How is 3 to the x different? I mean, looks pretty similar, right? What's different about it? Gets closer to the y-axis. Okay. Make these more different in color, sorry. Closer to the y-axis. How else can we say that? Steeper. Stretch, steeper, faster, right? If we're talking about this as growth, it's faster, more rocket shippy, right? Like it's got a bigger rocket motor on it, I don't know. It does the same thing, it just does it all faster, right? More pronounced, more severe. Why? The number's bigger, right? The base is 3 now. So if 2 to the x with base 2 hit all the powers of 2, right? So we went 1, 2, 4, 8. 3 to the x with base 3 is going to hit the powers of 3. So it's going to go 1, 3, 9, 27, and each of those is bigger than the corresponding power of 2, right? So you can see that if you looked at a table, the way it shows up on the graph is that it's steeper. For example, here when x is 1, 2 to the x we get 2, 3 to the x we get 3. Well, 3 is bigger than 2, right? And that gap between them just gets more pronounced as you go along because it's going to grow faster. What about 5 as the base? Same thing, but now the base is 5, so it's even faster. So if I look at these kind of all together, 2, 3, 5 as the base, what happens is we increase the base? It just goes faster, gets steeper, right? That's all. gets, becomes a sort of more pronounced, like, I don't know what you want to call that shape, almost like is that the way L's go? No, that's backwards, right?
Yes.
I'm sorry. I promise I know how to write stuff, but like you think about something too much, and you're like, is that right? Like whatever the opposite of an L is, right? But that shape just gets more pronounced as the base increases. All right, I'll throw on like, I don't know, 10 to the x, right? Like that's going to be even steeper. Does it change any of the, sort of vital stats back of the trading card type stuff? No. Domain's the same, the range is the same. They even have the same y-intercept because anything raised to the 0 power is 1. And they have the same horizontal asymptote. So none of this stuff changes. It just affects the shape a little bit. The same way that changing the slope for a straight line doesn't necessarily change where it is or how it works. It just changes how steep it is. Right? It's the same idea. So a lot of parallels to that stuff. Okay. Well, what if the base is something like 1/3? Flips it how? Over what?
Like an L now.
Now it does look like an L, yes. Thank you. I think. No, it does. Definitely. It reflects it which way? Over the y-axis, okay? And yeah, now it's the same shape, but let's see, that's 1/3, so there's 3, right? So it's the same shape, it's the same, steepness, like however we want to measure that. It's just decreasing instead of increasing, right? Did that stuff change? Domain range, etc. Those are all the same, right? Now the asymptote tells me more about what happens over here than what happens over there, right? But it's still the same horizontal asymptote. It's just that it fits the opposite side a little better. But everything else is the same. So it's just a reflection across the y-axis. Hey, what happens if you take something like 3 and raise it to the negative x power? How else can we write that? As a reciprocal. The numerator's 1, and I can write 1 as, a power of itself if I want to, because it doesn't change. So this is the same thing as that, just thinking about exponent rules, right? Like how you rewrite powers. This would be 3 to the x, the thing in orange, right? That function with a reflection. It's on the inside, so it's a reflection this way. That's why this does what it does. So similarly, 1/5 is going to be a reflection across the y-axis of 5 to the x. So it's going to hit all the same values, right? The nice points. If I was going to find a bunch of points for these by hand, 5 to the x, I would get powers of 5, right? I'd plug in 1 and 2 and 3, and I'd get the corresponding powers of 5. 1/5, I would do the same thing, only they'd be over here instead of over here, right? It's a reflection across the y-axis, so it's the same graph but backwards, right? Actually shaped like an L instead of the thing that I think is an L, apparently. I face the wrong way a lot, okay? I know that I can't keep using that excuse for everything, but I'm going to try anyway. But again, none of the domain, range, intercept, none of that stuff changes, right? Until we start moving things around. Yeah, I mean, if we were going to find... Oh, wait, no, sorry, I don't mean that. I mean 5 raised to a power, so 5 squared. So 5 to the x, 5 to the first is 5, 5 squared is 25, 5 cubed is 125. Yeah.
The same thing with 3. It's just the 3 is the base.
Right. Yeah, so just like anything else, right? Think about other times that you've, plotted a few points by hand to sketch something or get a feel for what a thing is doing. You pick nice values, right? You say, okay, I'm going to see what happens when x is 1 or 2 or 3, right? And I'm going to plug that in. I'm going to take the y value I get, and that's great. If I do the same thing here, the kind of y values I'm going to get are going to be powers of the base, right? 5 and 25 and 125. Okay, so if the base is larger, the function gets steeper. If the base is a fraction, apparently, maybe, then it does this kind of thing instead. What's the cutoff? If the base was 0, we'd be talking about 0 raised to the x, but 0 raised to any power is just going to stay fixed at 0, right? Okay, so the base being 0 isn't really very interesting. Like, nothing's going to happen there. The base cannot be negative, because if it's negative, then weird, squirrely stuff happens with the signs, right? Like, sometimes they're going to cancel, sometimes they won't. So this base value is never a negative number. So right now the base is about 4, right? And it looks about like that. And if I put 3 to the x and 5 to the x up there, this would be kind of right in between them, right in the middle. If I let the base be larger, the function gets steeper, right? If I decrease it, then it gets less steep. But if I look at the big picture, this still looks pretty much the same, right? But where do things flip over? At 1. Because what do powers of 1 look like? There's just 1, right? 1 to any power you want is still just 1. Okay, so if the base was 1, nothing interesting would happen at all, right? 1 to the x is just exactly equal to 1 everywhere. You just get that horizontal line then, y equals 1. If it's anything bigger than 1, though, even if it's just a little bit bigger, what it's going to do over time is grow, right? At a slower rate, right? Think about like interest rates and stuff like that on, like your bank account or whatever. If you have like something like a checking or savings account, the interest rate is very, very small, right? But every once in a while, you get that little thing that shows up in your balance that's like, hey, interest was paid, and you're like, oh, cool, an extra 4 cents, awesome, thank you, bank, for giving me that 4 cents. It's because the interest rate is very low, right? But it's still growing, right? And it's increasing. It's not money going away. So anything bigger than 1 is going to increase, is going to grow over time. Anything smaller than 1, even if it's just a little bit smaller than 1, if I multiply over and over again by 0.84, every time I do that, I'm going to get something smaller back than what I started with, which is going to cause the thing to decrease or decay. So these basically then fall into sort of 2 big like categories. Exponential growth, right? Whatever the function is getting larger over time. That happens anytime the base is bigger than 1. Or exponential decay, the reflection about the y-axis. That happens anytime the base is smaller than 1, and again, for reasons of sort of making things work and be consistent, the base can't be negative. So anytime it's between 0 and 1. So similar to, think about like when we talked about quadratics a few weeks ago. And just about every time we saw a quadratic show up, the first thing I asked was, hey, does this open up or does it open down? Right? Because we can tell at a glance, whether it opens up or opens down based on the leading coefficient. The first question to ask here for exponential stuff is generally going to be, is this growth or decay? Right? Is it a function that's increasing or is it decreasing? Because we can tell at a glance by looking at the base which one it's going to be. And then I know something about what to expect and what's going to happen going in. If I'm talking about, like the checking, like the banking account, right? I go into that knowing, okay, there's some interest being paid. That means we're talking about growth. That means it makes sense to ask a question like, hey, 10 years from now, how much is going to be in that account? Well, it ought to be more, right? If the only thing that's happening is the interest. Decay, well, some situation where things are decaying, I know that in the future I should have less stuff than I have now, right? Because it's decaying. Okay, so this, if you want to think of this as one picture or two, that's up to you. It's the same thing, just reflected, right? Just backwards. But that's the picture to have in mind for exponentials and how they work. And the domain and range, all that stuff that's written over there, that's the thing to have in mind, right? They're defined everywhere, but they only live, the range is just the upper half, and they've got that horizontal asymptote on the x-axis. Okay, 5 minutes. Okay. And all that's true up to the point that we start moving stuff around, right? As usual, like transformations move things, right? That can change the domain, the range, the intercepts, the asymptotes, all that kind of stuff if we move in that direction. So let's think about transformation stuff and try to figure out what we can figure out about this function. First, is this going to be something that's growing or decaying over time? Growing. How do you know? Basis 3. Bigger than 1. Yeah. Base is bigger than 1, so it's going to grow over time. Okay, so I know then that this function looks something like, make that better. That for starters. Now, what happens to it in terms of transformations?
Up 1, right 2, and stretch by a factor of 2.
Okay, so that times 2, that's definitely going to be a stretching factor, right? Here we're adding and subtracting. Those are going to be shifts then, right? Let's think about the order and where those happen though. Where is the x plus 1? Sorry, where is the plus 1? It's with the variable, right? It's grouped in with x. If I wanted, and you may need to sometimes for like calculators and stuff, you probably need to throw a set of parentheses around the x plus 1 to show that that whole thing is the exponent. So that's grouped on the inside then of this function's like argument, right? Where the independent variable is for this function. So that x plus 1 being on the inside is going to shift things, but it's going to affect things left to right. So plus 1 there is going to shift to the, since you're adding, to the left. The times 2, that's going to stretch vertically by a factor of 2. And then the minus 2, if we are thinking about like order of operations, that would happen last, right? First thing, stuff that's grouped, okay, that's grouped. Then exponents, okay, that happened. That determined the shape of the thing. Then multiplication, okay, that's that stretching thing. Addition, subtraction would be the last thing to happen, which is this. That's going to shift everything down then. Okay, so what we do then is we're taking this function, we're shifting it to the left, we're stretching it. So can I do that? So it's going to be like steeper, right? And then moving it down. Now, conceptually, that looks something like this then, right? What does that change about all of this stuff that we need to be able to find?
Changes
The y.
Domain doesn't change, right? That's good. Well, the range? Yeah, we moved it down, right? The range was 0 to infinity. It sat kind of parked just above the x-axis, but we moved it down. It's gonna change this also. It's also gonna change the y-intercept. And we didn't have an x-intercept before, but now we picked one up, right? Because I had this thing that, again, was parked just above the x-axis, but then I moved it down. Well, now it crosses the x-axis. Okay? So, we're out of time for today, but spend some time with that and kind of trying to firm up some of those details, right? Look for like where those things are. Try to find a couple of points, right? Either by taking points that were on the original function, right? Like on the paragraph 3 to the x and moving them around, or by picking a couple of x values and just plugging them in and seeing what you get. Right? Find a couple of points for that to track things, and then try this one as well. Okay? And we will pick up there on Thursday. I'll see y'all then. See ya.